All right, this is going to be our second lesson of 3.1. And as again, we're kind of working with exponential functions, but in this case, we're going to talk about a specific function called the natural exponential function. So this is the natural exponential function, and again, it uses something called the natural base, so this function is f of x equals e to the x. And so e is what we call the natural base, okay? And this is our natural exponential function. You can see we've started using this number e. So e can be approximated by two ways. So as a decimal, and again, you could type this into your calculator, but e is approximately 2.7182818828, and it never ends. It keeps going forever. But another way that we can describe that is we can just say that e could also be described by 1 plus 1 over x to the x. So below we've graphed those two lines. And again, so if you were to graph it, you would see, hey, my line keeps getting closer and closer and closer to y equals e to the x, but it's never going to actually reach it. That's an asymptote right there. So those are those two lines graphed. And so you can see that as x gets bigger, the line gets closer and closer and closer to that asymptote, but it's never going to reach it. If we look at some table of values, so again, I take this formula and I plug in 10, I get 2.59. If I plug in 100, I get 2.70. 1,000, 2.71. 10,000, 100,000, my numbers keep getting closer to 2.718. Again, that's that number as a decimal here. So that's kind of what this natural base is. And so again, you can use your calculator to evaluate that stuff. So if I take out Desmos, okay, if I click, there's a couple ways. I can go to the letters and choose E, or if I look on my function button, there's an e to the x right here. So say I want to the -2, I just go, okay, here's -2, perfect. I'm in my exponents. There's my answer. Maybe I wanted a decimal, so I go back to function and I say e to the 0.25, okay, enter. Again, using Desmos makes it very, very easy. You may have to graph these, again, so your exponent rules apply and basically are the same. So what I would recommend doing is if you needed to graph the function, let's say graph f of x equals 2e to the 0.24x. What I would do is I would make a table, so whatever x is, and then whatever my function equals. Maybe I start at -3, -2, -1, 0, 1, 2, 3. Okay, so then again, every time I'm going to plug a -3 in for x. I'm going to plug a -2 in for x. Again, I can just use my calculator. I can calculate these numbers out. And then I'm going to get, all right, if I have to graph this, I'm going to say, well, when I plug in a -3, I get 0.974, -2, 1.238, -1, 1.573, 0 is 2.0, 1 is 2.542, 3.232, 4.109. Say I take my graph paper, and I'm like, all right, here's x, -3, -2, -1, 0, 1, 2, 3, 1, 2, 3, 4, 5. And I'm just going to plot these points. So when I had a -3 in, I got a 0.97. When I had a -2, I had 1.23, -1, 1.5. 0 was a nice 2.0, 1 was 2.5, 2 was 3.2, and 3 was 4.1. So you can see that our line kind of has this upward progression because it is, again, an exponential function. So that's how I would graph it by hand. When does E become useful? And you may have heard of this, but E becomes super useful when we talk about compound interest, okay, and continuous compounding. So compound interest is how you can make a lot of money. So basically what it means is that you earn, if you like loan some money out, you earn money back in return for letting them borrow it. And so you can do it a certain amount of times per year. So we've got two formulas. So formula 1 is for compounding n times per year for, n compounds okay, and then that's going to be the formula A equals P1 plus R over N NT. And we'll kind of dig into these. And then your second equation is for continuous compounding. And that's going to be A equals P, there's that E, R times T. All right, so we're going to do a couple examples here and then send you on your way. So if I take a look and I say a total of $9,000 was invested. So total $9,000 invested at an annual interest rate. So annual rate two ends of 2.5% compounded annually. So those are the important things I need to know. Find the balance after 5 years. So find balance after 5 years. So I'm going to take my formula. Again, this is n compounds per year. So I'm going to take this formula and I'm going to plug some numbers in. So my formula is, again, A equals, so that's the account, or like the balance afterwards. P is called your principal, or the amount you start with. 1 plus R is your rate, and N is your number of compounds. And then again, the formula goes N times time. So let's kind of label this stuff. So we're going to say that this is called your principal, or your original amount. Principal. R is called the rate. So like your annual interest rate. So N is number of compounds. And then again, this is the same thing, number of compounds, and T stands for time. And then this is your, I don't know what you want to call it, account or final balance, end result. Okay, so plugging in these numbers for this problem, I want to find the end result. I want to know how much I have. My initial amount was $9,000, 1 plus the interest rate was 0.25%. So again, 2.5%. 2.5%. If I turn that into a decimal, I have to divide it by 100, which moves my decimal point 2 spots. So 0.025. That's going to be my decimal. So 0.025. And then again, the number of compounds it was compounded annually, which just means once per year. Again, my n is going to be a 1, and then my time was 5 years. So now we can start simplifying some stuff. Okay, again, well, I can't do anything outside my parentheses, but I could figure out what's 1 plus 0.025 divided by 1. Well, 0.025 divided by 1 is just 0.025. So now I have 1 plus 0.025. I can simplify that to just be 1.025. And then 1 times 5 is an easy 5. So from this point, I would use my calculator, and I would say, okay, I've got 9,000 in parentheses 1.025 to the 5th power, and that's going to be my answer. So after 5 years, I'm going to have $10,182.67. All right. Finding compound interest. This will be our last example for this problem. So a total of $12,000 was invested at an, so let's start writing this down. So total $12,000 invested at an annual interest rate. So interest rate 3%. Find the balance after 4 years if it was compounded. So 4 years if it was compounded quarterly and continuously. So 2 problems, quarterly and continuously. So if it's quarterly, we're going to do it the same way we did before. So I'm going to use A equals P 1 plus R over N to the N times T. So I'm just going to plug in. I've got $12,000 to start. 1 plus my rate is 3%, which means if I move it 1, 2 as a decimal, it's 0.03. So 0.03 over, not 1 this time, because quarterly, if you think about that word quarterly, means 4. We have 4 quarters in a season, so I'm going to put a 4 underneath here. And then again, my rate, or my n is 4, and my time is also 4. So as I simplify, I'm going to get 12,000 divided by, I'm going to have to use my calculator for this. So again, let's see here, 0.03 divided by 4 is 0.0075 plus 1. That didn't work. Plus 1. 1.0075. So I'm going to say 1.0075. 4 times 4 is 16. So now I'm going to take this equation and plug it into my calculator. 12,000 parentheses 1.0075 to the 16th power. And so my answer is going to be 13,523. And if you round that 0.905 up, it's going to be 91 cents. Now, continuously, if you remember, continuously has a different equation. So we need to do a separate equation to solve this one continuously. So A equals P E. We got to use that natural base E to represent continuously, which means, again, every second it's increasing. It's just constantly increasing. It's never stopping. P is my principal amount. That stays the same. E, we don't know. We'll never be able to fill out E, but we do know that our rate is 0.03 and our time, so 0.03, and our time was 4 years. So let's figure out what's 0.03 times 4. 0.03 times 4. 0.012 or 0.12. So equals 12,000 e to the 0.12. And now that's what I'm going to plug into my equation. Nope. Go to function, hit the E, and then you can type in 0.12, and there's going to be our number right there, $13,529.96. So you can look at the difference and say, hey, it may not seem like a lot, but simply by how they structured their interest rate, they gained an extra $6 for free. Now, again, imagine that happening for 40 years rather than 4 years. Or imagine that your interest rate was 2.5% rather than 3%. It can really alter and change the problem.